In this video, we're going to talk about section 1.3 exercises from Apex Precalculus. And we're going to talk about factoring and expanding. And so our first question here says, in your own words, explain the relationship between factors and roots. When we set each factor equal to 0 and solve, we're going to get the roots or the solutions to the equation. Usually it's a quadratic equation, not always, but we're going to be able to factor something even if it's not an equation. Some examples of something that's factored already would be number 6 down here, and see how it doesn't have an equal sign. But if this were a function that was y equals, or f of x equals, and in this case f of a equals, or f of b equals, then I could set each of those equal to 0 and solve. So I'm going to want to expand that one down there, though. This one would be f of k. See that's f of k equals. So if I could factor this f of k in number 15, those would be the factors. If I set each factor equal to 0, I'd get the zeros, or the roots of this function, of this equation. So that's the difference between that. We'll talk about that in a little bit. If x equals 2, x equals 5, and x equals -1 are the only roots of a function f of x, what are the factors of f of x? So again, they're saying x equals 2. We're going to go backwards and subtract 2 from both sides so that the factor is equal to 0. There's the one factor there. There's my second factor. There's a third factor. So there's a 0 factor property that says if x equals a is a 0 or a root, x minus a is a factor. That's our 0 factor property. So our factors are going to be x minus 2, x minus 5, x plus 1 for f of x equals. And we don't know how many times they appear as a factor. We're going to assume one time because it didn't tell us differently. What does it mean for a quadratic to be irreducible? It means that it can't be factored across the reals. So it's going to have zeros or roots that are from the quadratic formula that have a square root left in them, or it may have complex answers to them that have a square root in them, square root of a negative number. But we're going to see something like x squared plus 4 would be an irreducible quadratic because that doesn't factor across the reals, or x squared plus 2x plus 2 is an irreducible quadratic because it doesn't factor across the, I said the reals, I meant the rationals. It doesn't factor across the rationals. Factors across the reals, but not the rationals. I'd have to have square roots involved here. So I'd have to say that this was, if I set that equal to 0, then I'd have to say, actually, this one doesn't factor across the reals. I was right when I said that the first time. And this one, if I set it equal to 0, they don't have to come up with imaginary answers, though. I could get answers that would be like, something like that. So if I did that, and just show you what that might look like. That would be an irreducible quadratic. because it wouldn't factor over the rationals. What's the maximum number of factors that g of t equals t to the 6th plus t to the 4th minus 2t squared plus 1 could have? The maximum number is 6. That's the fundamental theorem of algebra, is that for an nth degree polynomial, it can have at most n factors to it, n linear factors. I think that one's probably not going to have 6 real answers to it though, but I'd have to check it and see. What's the maximum number that g of t equals t to the 6th? Okay. Hang on, they want us to use Descartes' rule of signs here. Got it. So we're going to have positives, negatives, and complex. I'm just going to show you this. So for number 4, the number of sign changes in the original is 1, 2. If I find the number of sign changes in the, if I plug in negative t, because it's an even function, it's going to have the same number of sign changes. So it's also going to be 2. So there's going to be 2 complex that it's going to get, that these are going to be irreducible quadratics here. So the maximum number here of linear factors that I could get in this one would be 4. I'm not ever going to get linear factors from that because, so the maximum number here is 4. I could have 2, 0, 4 or 0, 2, 4, or I could have 0, 0, 6. Are all also options, but the maximum number of linear factors that I'm going to get from that is going to be 4. All right, let's look at this one that is plus, minus, complex. So number of sign changes there is again 2 and 2 because that is still an even function. So this is going to be 2. It's going to be the same thing, that's going to be 4. I have the same setup here, that this could be any of those. Now the maximum number of roots, that includes the complex roots. So the maximum number of roots that it can have, which includes all the complex numbers, is going to be 6. For number 5. So number 4, the maximum number of linear factors is going to be 4. For number 5, the maximum number of roots is going to be 6. And this is the fundamental theorem of algebra. Tells me that it's going to be the degree of n there. There's going to be exactly 6 roots to it, real or complex. It doesn't say anything here about rational or real or anything like that. So I'm going to assume that's talking about all of them, even complex. All right, we're going to expand number 6. B plus 5, A minus 2B. I'm going to leave this 3A on the outside first because it's the easiest thing to multiply in later. We're going to do first outside, inside last here, 2AB minus 4b squared plus 5a minus 10b. Now we're going to multiply every term by 3a. So we 6a squared b minus 12ab squared plus 15a squared minus 30ab. That's it. That's the expanded polynomial. Number 7, 2t plus 7 squared. I've already talked to you about a perfect square trinomial, so I'm going to square the first term, multiply first and the second and double it, and then square the last term. 2 times x squared plus 3x plus 4 is 2x plus 3. So I'm going to leave the, let's just multiply the 2 times the last one for right now. It doesn't matter what order I do the multiplication in. There it is. So I'm going to take x squared times 4x, get 4x cubed. I'm going to get plus 6x squared. Now 3x times 4x is 12x squared. 3x times 6 is 18x. 4 times 4 is 16. 4 times 6 is 24. I'm going to add 4x to the third plus 18x squared plus 34x plus 24. 9. T squared minus 3t plus 1 times 2t minus t squared plus 2 times 2t minus 3. So we're going to have to multiply it this way, distribute. This is 2t to the third minus 6t squared plus 2t. We're going to have to minus, and then this is going to be 2t to the third minus 3t squared plus 4t minus 6. It's on the inside. Remember, all the signs have to change. So this is 2t to the third minus 6t squared plus 2t minus 2t to the third plus 3t squared minus 4t plus 6. And there we go. Negative 3t squared minus 2t plus 6. That was number 9. On to number 10. X to the third plus x minus 2 times 2 minus quantity 2x plus 1 times the quantity 3x squared plus 1 is going to be 2x to the third plus 2x minus 4 minus quantity 6x to the third plus 3x squared plus 2x plus 1. I went ahead and wrote it in descending order to start off with, that I'd get the x to the fourth, or x to the third term, and then the x squared term, and then the x, and then the constant. So I didn't write FOIL in the way that I normally would. This is going to be 2 minus 6 x to the third minus 3x squared. I don't have an x squared term over here. Plus 2 minus 2x plus a negative 4 minus 1 be a negative 4x to the third minus 3x squared. That's 0 minus 5. Number 11. X squared plus 3x minus 1 times 4x plus 2x squared minus 5 times 2x plus 3. It's going to give us 4x to the third plus 12x squared minus 4x plus 4x to the third plus 6x squared minus 10x minus 5. 4 and 4 make 8. 12 and 6 make 18. Negative 4 and negative 10 make negative 14. Minus 5. Variables don't really matter. Some variables are easier to write than others. We're going to stick in a theta. We've talked about theta in another video and how it usually represents an angle. Exponents before multiplication. Theta squared squared is going to be theta to the fourth. 4 times 2 is 8 theta squared plus 16 is 2 theta. We're going to have 6 theta times theta to the fourth plus 8 theta squared plus 16 is going to give us 6 theta to the fifth plus 48 theta to the third plus 96 theta. Now we're going to go the other way and we're going to factor each of the functions completely. So we're going to start off with g of x is equal to 4x squared plus 4x plus 1. This is typically what you're going to be doing. You're not going to be doing nearly as much expanding. I recognize this to be a perfect square trinomial. Maybe you don't. So we're going to start off factoring it into two binomials since it's a trinomial. It's going to be in terms of the middle variable here, x. I'm going to have x and x here. I'm going to try 2 times 2 is 4. Factors are the same. Sign, both positive. Same sign, both positive. And factors of 1 are 1 and 1. 2 plus 2 is 4. So I can write this as 2x plus 1 quantity squared. Y of z is equal to z squared minus 7z plus 10. So we're going to write this as two binomials. Signs are the same, they're both negative. Factors of 10 that add up to be 7 are 2 and 5. So that's fully factored. Let's look now at number 15. It asks us for f of k is equal to k to the 4th minus 27k. First thing that we're going to do here is pull out the common factor of k, and that leaves us with k cubed minus 27. This is called a difference of cubes, and it has a special formula that says that a cubed minus b cubed is going to be equal to a minus b times a squared plus ab plus b squared. Similarly, a cubed plus b cubed is going to be equal to a plus b times a squared minus ab plus b squared. We talk about that in the MTE6 video. So go back and look at that if you'd like to. Just going to go ahead and factor it based off of the fact that this is k cubed and this is 3 cubed, that this is going to turn into k minus 3, k squared plus 3k plus 9. This here is going to always be an irreducible quadratic. Don't try and factor that anymore. It's actually going to have two complex solutions to it. When you get a choice to, when you have something that's a 6th power, that you can do difference of squares or difference of cubes first, do the difference of squares first before you do the difference of cubes, because otherwise you're going to get stuck and think that something can't be factored or not be able to see how to factor it more. Okay, they're just being a little pretentious with number 16. They're calling the function name theta and they're sticking in the variable gamma. So they're going to say 6 gamma squared minus gamma minus 2 is going to be what theta of gamma is. So this is going to be now factors of 6, I'm going to say are probably 3 and 2. Factors of 2 are probably 2 and 1. I need to make it have a difference of 1, so I'm going to put 2 and 1 so that 4 and 3 have a difference of 1. And I need the bigger one to be negative, so I want a -4 and a +3. If you don't like that method and want something that's not guess and check, let me show you a way to do this where there's no guessing involved. We again go over this in MTE6. I'm going to take a times c is going to give me -12. I want all the factors of -12 with the bigger factor being negative. So 1 and -12, 2 and -6, 3 and -4. And I'm done because once I start making the positive factor bigger, then I'm not going to get a negative number on the inside. Which of these add to give me -1 in the middle? Those do right there. So I could make this. Now I'm going to split it into the sum of these two like that. Imagine there's that plus sign in between there. I'm going to pull out the greatest common factor from the first pair. And I'm going to pull out the greatest common factor from the second pair. And these need to match each other because of this table working the way that it did, or I did something wrong. So signs and everything have to match each other. When I have a negative for this third term, I must pull a negative out so that the positive sign matches one another. So this can be 2 gamma plus 1. I'm left with 3 gamma minus 2. And there we go. Same factors. I just wrote them in the opposite order. But there's 3 gamma minus 2. There's 3 gamma minus 2. There's 2 gamma plus 1, 2 gamma plus 1. So this is called the AC method. This is called the guess and check method. I did. Both are appropriate methods. If we're going to prove that something is prime and can't be factored, though, we're going to have to use the AC method most of the time. All right, let's talk about number 17, which says x of z is going to be equal to 3z cubed plus 6z squared minus 24z. We always start off with the greatest common factor. It's again something that we talked about in MTE6. So 3z is my greatest common factor, z squared plus 2z minus 8. Factors of 8 that have a difference of 2 are going to be 4 and negative 2. 4 minus 2 is a positive 2. 4 times a negative 2 is a negative 8. So there's my fully factored form. Number 18 is going to be a sum of cubes, x cubed plus 8. I have to break that down into x plus 2 times x squared minus 2x plus 4. I talked about that formula just a minute ago. Number 19. F of x is equal to 2x cubed minus x squared minus 5x minus 2. When I have 4 or more terms, I'm going to try, if I can, to factor by grouping, but there's nothing here that looks really nice for factoring by grouping. So I am stuck with the rational root theorem here. So I'm going to give myself some extra space here. The rational root theorem tells me to take factors of the last number. So dealing with plus or minus 1 or 2. Factors of the first number, also plus or minus 1 or 2. So I'm going to start off with dividing by this first number here. 1 divided by 1 is going to be 1. 2 divided by 1 is going to be 2. Then I'm going to switch to dividing all the things in the numerator by the second number. 1 divided by 2 is 1/2. 2 divided by 2 is 1 again, so I don't have to write that down. So I've got 6 possible options, but I know that only 3 of them can work. Let's go ahead and let's make my chart for Descartes' rule of signs here, just to be careful, make sure that I'm thinking smarter, not harder. So I've got one sign change here. If I find f of negative x, that's going to give me negative 2x to the third minus x squared plus 5x minus 2. I'm going to have 2 sign changes there. So that tells me that I have to have a positive, but I don't necessarily have to have any negative answers. So once I find my one positive answer, I'm done, and I don't have any more positive answers to check. Let's go ahead now and let's see if start testing these positive answers. These are all my possible rational answers, by the way. It doesn't help me out with any irrational answers that I might have. So, but if I use up all my rational answers that are possibilities, I have to have irrational answers. That's not 0. My synthetic division should give me my function value when I'm done. So that's not right. 2, -1, -5, -2, 2, 4, 3, 6, 1, 2. There we go. Okay, so that tells me that this factors into x minus 2 times 2x squared plus 3x plus 1. That's easier for me to factor. That's 2x and x and 1 and 1. 2 plus 1 is 3. So that means that my roots here were 2, -1/2, and -1 in any order. It doesn't matter which order they are, but I used synthetic division to reduce it into a factorable quadratic. Stopped once I got to a quadratic and then used my regular factoring techniques. If I could not have factored this quadratic, then across the rationals, then I would have used my quadratic formula to find the irrational zeros of it and use my rational root theorem, my zero factor property, to write it as a product of linear factors, even if those zeros were irrational. Let's go ahead and look at number 20. Okay, again, there's not going to be a common factor that we're going to pull out that's going to leave us with the same thing on the inside, because there's no factors of 5 that are also factors of 24. I'm not even going to bother with that. So factors of 24, 1, 2, 3, 4, 6, 8, 12, and 24. It's nice that there's only 1 down there. So my possible rational zeros are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 12, plus or minus 24. I'm going to use Descartes' rule of signs again, just to help myself out. There's 1 sign change, 2 sign changes. F of -y is going to give me -y cubed minus 5y squared plus 2y plus 24. There's going to be 1 sign change, 0. So this time I'm not guaranteed any positive answers. So I'm probably going to check my negative answers first here. So let's start with 1, -5, -2, 24. -1 doesn't seem like it's going to work. I just tested it in my head. -2 does seem like it's going to work to me. So this is going to factor into x plus 2 times x squared minus 7x plus 12. Factors of 12 that add up to be 7 are going to be 3 and 4. So my factors are -2, +3, and +4 my zeros. These are my factors. I put x's there, it's actually y's. Make sure you are consistent with your variable. The function was in terms of y, so don't change it to x's. Keep your y's there. All right. Determine the difference quotient. So we're back to difference quotients. Again, I told you that that was something that was going to be important. G of t is going to be t cubed plus 1. They're now giving us things that are higher powers for us to deal with. I'm going to tell you about Pascal's triangle right now. It's going to help me with these difference quotients. I don't see anything higher than the 3rd power. So this is when n is 0, n is 1, n is 2, n is 3. So these are going to be my coefficients here, and I get them by bringing down the 1s on the outside every time. Then 1 plus 1 is going to give me 2, 1 plus 2 is 3, 2 plus 1 is 3. and I can make more rows of Pascal's triangle that way. So this tells me that when I have g of t plus delta t minus g of t over delta t, that g of t plus delta t is going to be t plus delta t cubed. It's going to give me t cubed plus 3t squared delta t plus 3t delta t squared plus delta t cubed plus 1 from the function minus my original function of t cubed minus 1, because it's minus the whole thing, all divided by delta t. So this is going to be reduce each of the powers of delta t here. This is going to be 3t squared plus 3t delta t plus delta t is going to be what my difference quotient here is. So Pascal's triangle is going to help us a lot here. Number 22, 2x squared minus 5 be 2 times, let's just go ahead and do the expansion, x squared plus 2x delta x plus delta x squared minus 5 minus 2x squared plus 5. All that's over delta x. This is going to be 2x squared plus 4x delta x plus 2 delta x quantity squared minus 2x squared plus 5. There was a, let me just go ahead and say this made a 0 there. Then this makes a 0. And then I'm reducing the power of delta x here. And there's my difference quotient for number 22. Number 23, f of x is equal to x cubed plus x squared minus x. This is really gross. It's going to be big and nasty. I'm going to go ahead and find f of x plus delta x separate from everything else. So this is going to be x to the third plus 3x squared delta x plus 3x delta x squared plus delta x cubed plus, now I've got to do it with the squared, so that's x squared plus 2x delta x plus delta x squared minus x plus delta x, so minus x minus delta x. So got a lot of terms here to combine. So we've got some, everything here should be degree 3, everything here should be degree 2, everything here should be degree 1. None of the terms are going to be like terms that combine with each other. So now we need to subtract the original, negative x cubed minus x squared plus x. So these terms without delta x's in them here are going to go to 0. Just those terms and only those terms. So f of x plus delta x minus f of x is going to be 3x squared delta x plus 3x delta x squared plus delta x to the third plus 2x delta x plus delta x squared minus delta x. We're going to be dividing all that by delta x so that we reduce the power on all of it. going to give us 3x squared plus 3x delta x plus delta x squared plus 2x plus delta x minus 1. So that's it. Looks gross. That's okay. So this is going to be dependent both on x and delta x, just like some of the other problems that we did in the last section. Number 24 is going to be g of x is equal to 4x squared plus 2x. So we're going to find g of x plus delta x minus g of x divided by delta x. It's going to give us 4 times x squared plus 2x delta x plus delta x squared plus 2x plus delta x minus 4x squared minus 2x all over delta x. It's 4x squared plus 8x delta x plus, this is a parenthesis here, 4 delta x quantity squared, like that, plus 2x plus 2 delta x minus 4x squared minus 2x. All that's over delta x. So our 4x squared and our negative 4x squared make it 0, or 2x and our negative 2x make it 0. We're left with 8x delta x over delta x plus 4 delta x squared over delta x plus 2 delta x over delta x. It's going to be 8x plus 4 delta x plus 2. All of those are unlike terms. Get very comfortable with doing that. That's going to be the most calculus-y thing you do in pre-calculus. Now we're going to find all the roots of the given function for number 25. 4x squared plus 2x. Greatest common factor is 2x. 2x times 1. We're going to set each factor equal to 0. We're going to solve. So our solutions, our roots are -1/2, 0. I'm just going to write them in a solution set like that. That's what these braces are for. Now we've got f of x is equal to x cubed plus x squared minus x. We're going to factor out the x. X squared plus x minus 1. I don't see any factors of 1 that are going to add up to give me 1. So I'm probably going to have some either irrational or complex roots here. Let's use the quadratic formula on the second piece. X is equal to -b plus or minus the square root of b squared minus 4ac all over 2a. 1 plus 4 is 5. So we have first root is 0. Our second root is -1/2 plus root 5 over 2. Our third answer is negative 1/2 minus root 5 over 2. You could also have written x2 as negative 1 plus root 5 in the numerator, all divided by 2. You could have written root 3 as negative 1 minus root 5, all divided by 2. It doesn't make any difference. They're the same answer. So those are my 3 zeros, or my 3 roots to my equation in 26. 27 says y of x is equal to 4x squared minus 5. We're going to set that equal to 0. And I'm just going to go ahead and factor this with a difference of squares. This is going to be 2x plus root 5. This is going to be 2x minus root 5. Root 5 squared is the only thing that gives me 5. So I'm going to set each factor equal to 0. And solve. 2x is equal to root 5. X is equal to root 5 over 2. Or 2x is equal, this is negative, is equal to root 5. X is equal to root 5 over 2. This is positive. So my solution set is negative root 5 over 2, positive root 5 over 2. Factor the given function and relate the factors with the roots found in the exercises above. So we already did that. So let's go back and factor this. 2x times 2x plus 1. So this is the factor that generated the answer x equals 0. This is the factor that generated the answer x is equal to negative 1/2. It'll be trickier to factor number 29 if we want to factor into linear factors, because we're going to have some square roots involved. But this is going to be x to the third plus x squared minus x. This is x times x squared plus x minus 1 when we factored it. This was the factor that generated the root x equals 0. This is the one that generated the factors x equals negative 1 plus or minus root 5 over 2. So if I want to turn those into linear factors, though, let's solve here for the two factors. Negative 1 plus root 5 over 2 equals 0. I'm sorry, equals x. X equals negative 1 minus root 5 over 2. So let's multiply by 2. 2x equals negative 1 plus root 5. 2x equals negative 1 minus root 5. This is 2x plus 1 minus root 5 is equal to 0. 2x plus 1 plus root 5 is equal to 0. So I could factor this into x times 2x plus 1 minus root 5 and 2x plus 1 plus root 5. And this one would be the one that would generate the answer of x equals negative 1 plus root 5 over 2. And this is the one that would generate the answer of x equals negative 1 minus root 5 over 2. So I can write it as a product of linear factors, even though that's not factorable across the rationals. I still can use a quadratic formula along with the zero factor property to factor it more completely. Then number 30, I factored it already when I answered the question into 2x plus root 5 and 2x minus root 5. And this is the one that gave the answer x is equal to negative root 5 over 2. And this is the one that gave the answer to x is equal to root 5 over 2. So that is everything for this section. Let's review our factoring techniques really quickly. We have a difference of two squares that's going to factor like this. We have a difference of cubes that's going to factor like this. We have a sum of cubes. It's going to factor like this. We get into a difference of force that's going to break up into a squared plus b squared times a squared minus b squared. That's going to be a squared plus b squared times a plus b times a minus b. This is going to continue to break down. We don't usually talk about a squared plus b squared at this point in the class, but I'm going to talk about it right now. We're going to talk about something called imaginary numbers, which involve the square root of -1. So this is going to break down into a plus bi and a minus bi. We talked about these i's in MTE 8 and MTE 9. Material. So go ahead and check that out if you're unsure about what a complex number is. You're supposed to have had some exposure to it in Algebra 2 before you take pre-calculus, so that that's not a completely foreign concept to you when you see complex zeros or complex roots to a polynomial in this class. All right, that's everything for now. Oh, I did want to mention, sorry. This breaks down into a perfect square like that because we're going to be completing the square later. This also breaks down into a perfect square for when we're completing the square in a little bit. Okay. See you next time.